Hello, everyone, and thanks for joining us. Today's webinar is focused on showing you how you can deploy and operate SQL Server on AWS effectively. We will take a slightly different approach, focusing on the best practices and recommended deployment patterns that have developed over the years. Many of these are in line with vendor recommendations and what customers should also be doing regardless of where they deploy SQL Server. And I'm sure a lot of them will look very familiar to you as well. Before we dive in, I'd like to briefly outline what the deployment options on AWS are. As you may already know, AWS has two services that can be leveraged to run Microsoft SQL Server. Amazon RDS, which stands for Relational Database Service, which is a fully managed service that takes some of the administrative tasks off your shoulders. Things such as backups, patching, high availability, or configuration management. This allows you to focus on the more valuable activities for your business, like schema design and optimization. Now, because of these benefits, we recommend you consider this option first. On the other hand, Amazon EC2, which stands for Elastic Compute Cloud, lets you run SQL Server where you have full control of the instance running your database engine and associated services. You trade off some of the management aspects as more of the administrative tasks fall under your area of responsibility. But either way, it is the same database engine of SQL Server that's running in RDS and on EC2. As a result, the feature set is similar between the two options. The same popular versions and editions are available for both EC2 and RDS, and you would use the same native tools you're familiar with to interact and manage both. Things like tools like SQL Server Management Studio. The authentication and encryption capabilities are also largely the same. The differences are in line with the managed nature of RDS. For example, on EC2, because you can install SQL Server yourself, you can bring legacy versions of the software to AWS. On the other hand, deploying a highly available configuration of SQL Server is not trivial, and RDS makes that really easy. We manage the entire deployment and operation for you, whereas on EC2 you would have to deploy it yourself using things like always-on availability groups, mirroring, or other similar technologies. RDS provides automated backups with point-in-time restore, consistent configuration management via parameter and option groups, and automated patching. On EC2, you'll need to install third-party tools or run specific database maintenance plans to achieve similar results. Now, on the other hand, because RDS is a managed service, you don't have full control of the instance. You cannot browse the file system, remote desktop into that RDS instance, or leverage the sysadmin role. And as such, certain features may not be available, such as database mail or MSDTC. And while you can use RDS as a data source or target for SQL Server reporting services or SSAS or SSIS, the services themselves cannot run on the RDS instance itself. So, as you're conducting the evaluation of which option aligns best with your application requirements, also keep licensing in mind. Whether you decide to use RDS or deploy your own SQL Server on EC2, you can pay for the SQL Server license, part of the service cost, or you can bring your own license. We call that BYOL. Now, using SQL Server under the license included model is very easy. You just provision an EC2 instance from an Amazon machine image, which is a template, that includes SQL Server. The software is already installed, and much like With any other AWS Marketplace AMIs, the licensing price is baked into the hourly rate for that instance. With Amazon RDS, the process is similar. You just tell us that you want to use the license included model. This is a great option if you don't have an EA with Microsoft or you don't run your SQL Server permanently, such as spinning up SQL servers for transient ETL jobs or scaling your resources up or down based on predictable demand, workday operations versus nighttime operations. Now, if you have license mobility through software assurance, you can bring those licenses to AWS as well. But you need to complete a license benefit verification with Microsoft. Once completed, you can simply install SQL Server from scratch on EC2 or pick the bring your own license option at launch in Amazon RDS. If you need to have an HA solution and the secondary instance is truly passive, meaning it's not a read replica, you would not need to license that node, providing you with cost advantages. Also, using EC2 dedicated hosts, you may be able to bring other per core or per socket licenses to AWS, as long as you're running those on EC2 dedicated hosts. So using your own licenses can also result in cost benefits depending on your licensing relationships with Microsoft. Okay, so now that we know about the available options, let's dive deeper into the best practices for SQL Server running on EC2. First, we'll spend a few minutes discussing specific recommendations around storage performance. By far, we see storage optimization to make the most amount of difference, ensuring customers deploy and operate SQL Server successfully. We'll also cover high availability and a few other key topics. In AWS, there are two main categories of block storage. The most pervasive being EBS. This is network attached block storage. Over the years, feature enhancements to this service has brought it to the point where performance can exceed that of typical direct attached storage in many cases, while offering better data durability. EBS is available for all instance types, and most current generation EC2 instance types support EBS optimization, either by default or as an option. EBS optimization provides a dedicated channel for network storage I/O, eliminating potential contention with other network traffic from that instance. There are three key performance drivers for EBS that are really important to remember. The bandwidth capacity refers to the size of the dedicated channel. It includes the maximum amount of storage I/O traffic that the instance can achieve. The larger the instance type, the larger the channel, so you should match the instance type with the aggregate storage I/O needs of your workload. Your volume, your EBS volume itself, can only handle a maximum number of output operations per second. The actual value depends on the volume type and the size of the volume as well in certain circumstances. Think of it as a freeway. There's only so many vehicles you can fit on it at any given point in time. And just like vehicles on a freeway, IOPS can have different sizes. And just like a freeway can only effectively handle a set volume of traffic, regardless of the shape or size of the vehicle, so do volumes. There is a maximum throughput that a single volume can achieve. And at any given point in time, any of these three drivers can act as a ceiling to the maximum achievable I/O performance on your SQL Server instance. There are 4 current generation types of EBS volumes, not counting a legacy magnetic type. 2 are SSD-based, designed for general and high-performance use cases with random or mostly random I/O. The other 2 are magnetic, designed to provide high throughput for large sequential read and write operations. As we'll see in a few slides, all have a place in the design of a SQL Server on EC2 solution. In general, for data and log I/O, pick general purpose SSD storage, if the workload is variable. For high performance use cases, where the workload pattern is constant and you need high levels of I/O and throughput constantly, pick provision IOPS. Magnetic volumes are useful in a supporting role for backup volumes or similar use cases. The other type of block storage in AWS is instance storage. These are drives directly attached to the EC2 hosts and made available to your EC2 instances. For current generation instances, instance storage is offered in specific instance families designed for high-performance use cases. The cost of the drives is included in the hourly rate of the instance. They also have some very important characteristics. Because the storage is physical, hardware failures can cause data loss. So you would be responsible for designing a solution that protects against that, or at least mitigates the effects of drive failures. Also, if you as a customer stop the instance using our APIs and then start it again later, the instance will come back on a different host. And your instance store data does not persist that cycle. So it's up to you to ensure data durability for these types of cycles. Data does, however, persist soft OS level reboots, or if we have to restart your instance for underlying host maintenance. And these volumes must be allocated at instance provisioning time and cannot be added later. But the advantage of using instance storage is that you can get higher aggregate throughput and I/O performance without going over the network. And that reaches a top aggregate performance of 3.3 million IOPS on the i3 16x large instance type. So quite significant. Along with better understanding of storage options on AWS, knowing your workload pattern will likely be key to successfully planning your SQL Server storage. Like in a traditional data center, benchmarks, load tests, query profiling can all help determine the right throughput and IOPS needed for your storage subsystem. So enable EBS optimization if it's not already enabled by default, and use an instance type that supports the desired throughput and IOPS you determine is needed based on such testing and profiling. Format your volumes with a 64K allocation size. There's a common misconception that SQL Server generates 64K I/O because the extent size is 8 pages of 8 kilobytes. It certainly can generate I/O of that size, but the various I/O optimization processes of the engine generate I/O both smaller and larger than that. The average I/O size tends to not exceed 64K though, hence the alignment with the file system allocation size. Also create a single volume for data and logs. This one is a bit more counterintuitive, especially given that in the data center world, the recommendation is mostly the opposite. In a data center, you have dedicated channels for different block storage devices, so it makes sense to saturate each channel individually. In AWS, EBS optimization provides a single dedicated channel, so unless there's other reasons to separate them, they all will consume capacity from the same pool. Then, stripe multiple volumes into a RAID 0, into a software RAID 0, to get more performance than a single individual EBS volume can provide, assuming your instance bandwidth channel actually has the capacity to handle that I/O. Now to the right, you will see an example drive layout for SQL Server common with our customers. The boot drive holding the OS and applications, but no data, uses a general purpose EBS volume. Data and logs are on a single striped EBS volume using provision IOPS, if the workload needs that level of performance. Backups for DR are stored on magnetic volumes. These are files that are typically written or read all at once and benefit from the sequential I/O throughput optimization. tempdb is sitting on instant storage if that's available. In practice, to maximize performance, such a configuration should be sized so about 90% of the available throughput is matched to the data and log volume, assuming, of course, tempdb is on instant storage and is actively used. From a backup perspective, this gives you the flexibility of leveraging EBS snapshots or shipping individual backup files to S3. And since we mentioned tempdb, here's a link to a striping solution by one of our partners that can be easily used to initialize and move the tempdb files to instant storage. You also want to use multiple tempdb files and stripe them across all drives available. If you decide to implement this optimization yourself, know that on instant start, our EC2 config service that's running on those EC2 instances will initialize the instant storage drives. This means they may not be readily accessible on boot, out of the box, once the SQL Server service starts automatically. So you want to switch that service to a delayed start or just start it manually yourself once you've confirmed that the volumes are initialized. And here is an example on how to do it manually. You simply alter the tempdb database and then grant the SQL Server service permission to that drive. Now, in AWS, having multiple availability zones is a game changer. An AWS region, which is your geographic boundary, includes multiple availability zones, which in turn are backed by multiple physical data centers. Availability zones are close enough to facilitate latencies, usually between 1 or 2 milliseconds, but are on different floodplains, power grids, and so on for added resiliency. In a traditional data center, most organizations would not even attempt to set up synchronous commit between data centers, simply due to the risk of high latency. But in AWS, synchronous commit across multiple availability zones isn't only practical, it's the norm. This means you can do automated failover across physical data centers, protecting you not only from instance-level outages, but data center-level outages. Now, the options you have with SQL Server on EC2 for high availability depend on the edition. For Enterprise Edition, the recommended solution is to leverage always-on availability groups. For Standard Edition, the options are a bit more limited. You can implement failover cluster instances using a partner-provided block-level replication solution, since AWS does not support shared volumes natively. And for SQL Server 2016, you also have access to basic always-on availability groups, which would provide you essentially with a passive secondary and comes with a few other limitations. So here's a basic setup for always-on availability groups. We have nodes in different availability zones, and a cluster configured for node and file share majority. The file share itself should be hosted on a different node, possibly in a different AZ, and it's not actually depicted on the diagram. There is a single always-on availability group listener, DNS endpoint, and Windows Server Failover Cluster manages resource failover. Now, this is configured for multi-subnet failover. And using the latest versions of clients in SQL Server, the failover can happen in the order of tens of seconds, usually less than a minute. If you use older clients, multi-subnet failover may not be ideal though. So you want to check the versions of clients and servers you are using and follow Microsoft's recommendations as far as multi-subnet failover there. Let's take this a step further. This diagram shows a multi-region multi-AZ design for SQL Server Always On. Automatic failover occurs between availability zones, but there is also an asynchronous commit replica over a VPN connection between two different regions, which allows you to do a manual failover at that level to an entirely different geographic region. And for folks running Standard Edition, you can use SIOS DataKeeper Cluster Edition to simulate shared storage. There's two distinct volumes that are seamlessly replicated at the block level to give the appearance of shared storage. Now, a lot of the recommendations above involve OS-level access. In RDS, because it's a managed environment, you don't have that level of access. We fully handle engine and instance configuration for you. And as with EC2, managing storage performance is also key for deploying SQL Server using RDS. High availability is managed by the AWS service, but it's important to understand the characteristics of that configuration. Additionally, because it's a managed service, a common ask is to learn more about the best practices to move and/or migrate data to and from the platform. So we'll discuss this briefly later on as well. Storage considerations for Amazon RDS are similar to what we discussed for EC2. Amazon RDS does not support instant storage, so you will only leverage network-attached block storage. The characteristics are similar to EBS SSD-based volumes, but there are a few aspects that deserve calling out. RDS for SQL Server storage cannot be scaled later, so you would have to plan the storage needs ahead. The limitation has to do with capabilities of striped storage in Windows Server. RDS database instances can be provisioned with a maximum of 4 terabytes of storage and a maximum of 20,000 IOPS. And as with EC2, throughput will depend on the instance class as well. And the I/O sizes are variable, so it is possible in many cases to reach maximum throughput before reaching maximum IOPS, given that the nominal performance characteristics of AWS storage is expressed in terms of 16 kilobyte block size I/O. And SQL Server often leverages or averages larger I/O operations. Now, to help with storage performance measurements, use the average queue depth metric in CloudWatch, which is our monitoring service. This represents I/O requests sitting in the queue waiting for the storage subsystem to service them. If the queue is 0, that means you're not pushing enough I/O to saturate. If, on the other hand, the number is high, I/O is likely a bottleneck for your SQL Server performance. Now, unlike EC2, where you have to set up your own HA solution using always-on availability groups or other mechanisms, Amazon RDS provides a fully managed, hands-off HA solution when you deploy your database instance in multi-AZ mode. This feature deploys two identical instances, a principal and a secondary, in different availability zones, with a witness in a third availability zone. It leverages synchronous SQL Server database mirroring technology to replicate data to the secondary instance. And in the event of a failure, the secondary instance is made available for continued operations. Multi-AZ mode is designed to mitigate failures at both instance and availability zone level. With Amazon RDS, your database instances are exposed using a DNS endpoint that we manage. That's what you use to connect to your database using client tools like SQL Server Management Studio. In the event of a detected failure, we stop database mirroring, promote the secondary to a primary, remap the DNS endpoint to the IP address of the new primary, and provision a new secondary node. All of this is done automatically. With a time to live of 60 seconds on the DNS endpoint, the whole process is designed to take a few minutes from failure detection to recovery. All your application has to do is implement retry logic to keep retrying database connections until service is restored. In fact, you should test your application's ability to tolerate a failover by triggering one manually, a capability that the service offers. You should make certain that there are no client-side dependencies that would cache the DNS entry longer than anticipated, for example, or don't fail over as designed. Now, because we rely on Microsoft database mirroring technology, write-heavy workloads may see a performance impact, as data changes have to be confirmed both by the principal and secondary nodes of the cluster, effectively a two-phase commit. Furthermore, mirroring may result in actually higher I/O load on the secondary for write-heavy workloads, or bursts of such load. So you want to plan storage performance according to the needs of the secondary node as well, since both nodes are provisioned in that cluster and they're all identical. Now, just because RDS is a managed service, it doesn't mean your data is locked in. There's many ways to move data to and from Amazon RDS for SQL Server. You can leverage SQL Server's native backup and restore functionality, and I'll cover this in more depth shortly. You can always use the publishing wizard or import and export wizard to simply get the data in flat T-SQL files and then load it up using the SQL command line. Although that's not usually the most effective way for fast changing or large data sets. For advanced use cases, you can leverage the AWS Database Migration Service, or DMS for short. This tool is especially useful if you want to achieve near zero downtime migrations, or you want to deploy read replicas of your master databases in a separate region. It handles the initial load of data and performs change data capture so you can keep up with changes asynchronously. Although CDC for RDS SQL servers is currently only supported inbound and not outbound. It's also highly available, so your replication jobs can run on an ongoing basis. And it supports even heterogeneous migrations between different database engines, from MySQL or Oracle or Postgres to SQL Server, for example. And the location of the databases can also be different. Some of them can be on-premise, on EC2, or on RDS. So it's really a very flexible tool to move data to and from SQL Server running on RDS or EC2. And finally, you can leverage the AWS Marketplace where our ISV partners offer third-party data movement solutions and tools as well. So let's see how import-export using native back files works in RDS. Since it may be a little bit different than what you're used to. First, keep in mind this feature only works with full backup files. To use native back file import and export, you need a couple of prerequisites. You need an RDS database instance first and foremost, but you'll also need an S3 bucket to store and load back files. Remember, you don't actually have OS level access to the RDS database instance itself, and you need a database option group authorizing access to that feature, where you'll specify what bucket you want to use and an IAM role that RDS can assume and get permission to actually read and write files to that bucket, along with the desired encryption settings. And then finally, you'll need a SQL client to run the stored procedures commands. To facilitate back file import and export, we provide a few stored procedures to manage the lifecycle of the jobs. Up on the screen are examples on how to back up, restore, and track the status of the jobs. You can also cancel an ongoing job. You can programmatically trigger these backups or restore jobs, but you won't be able to leverage SQL Server Management Studio's graphical wizards to backup and restore, as they only work with the file system. So you'll have to use these stored procedures.